Success. This is a crucial year for all of you, third year. Um I wish you all success in your own examination, your other endeavors, GATE examination if you're preparing, and obviously stay safe, everyone, and be careful. I hope you all have your visions and plans according to your, and you will accordingly carry out your actions. So that's my wishes to all of you, and also be attentive to the classes, and well wishes to your family members so that you can organize your things very well. Okay, so with this, let me start our first laboratory in this year, and the second laboratory in this session. Last lab, what we discussed about that how we are going to, uh, I just introduced, I think, about the practicals, how we do, what is the antenna is, and what we mean by radiation, and what is the practical concepts regarding this, isn't it? Have we started any practical before that? No. I think we didn't conduct any practical last year, right? Last class. Have we conducted? It is section B, isn't it?
No, sir.
Is it section B, right?
Yes, sir.
Shivraju? Yeah, we didn't conduct, right. So today we are going to start our practical, very interesting thing about the antenna pattern. Actually, when we conduct an experiment, what is our motive, what we want to verify, and that should be clear. Uh, there will be several antennas in this practical. The purpose for the undergraduate laboratory is to make you understand the fundamental about this. What is the designing of antenna? Not from the layman point of view only, to understand it very clearly about the basics. And in the virtual mode, we will be using software. Certainly, it will be student edition to try to develop it. It's not a mobile friendly software, CST microwave. I think you have done EMFT lab, right? Have you used the CST Studio Suite?
Yes, sir. We use it, sir.
Yeah, used it. Very nice. So I think you have downloaded version with you. If not, please download it. Student edition of Studio Suite. Today I will give you a demonstration of this one practical of designing a simple dipole antenna, and then we'll see how it works. Okay. It means we'll see the options of our output available. So I'm sharing my screen now.
Sir, 5250 print, sir.
What I will do with this absent man, don't be present. You're telling so after a long time. What was the issue with you?
No, sir, my power gone, sir. So Wi-Fi off, sir. So I joined with mobile data, sir. One second.
Okay, you joined with the mobile data now. Okay.
Yes, sir.
Janita ma'am,
Sir,
Janita ma'am, can you please consider him?
sir, I've
Coach,
submitted the attendance.
we submitted, right? For the next hour, it can be considered. We are taking the attendance real time. So next hour, you will be considered. There will be two attendance next to this. Okay.
Okay, sir. Okay, sir.
Okay. Please keep your peer group and the members informed about this in case of an emergency. To inform about attendance. Attendance can be any time. We'll take it at random. Sometime in the beginning, sometime in the middle of the class, sometime at the ending of the this thing. So that will be our way, and that's why you need to be aware, right? There will be no pre-information about the attendance. So that is that's why you should. I can understand few technical issues may happen sometime, but doesn't happen so frequently. So please be aware and keep your friends also informed, and write in chat box or uh, immediately inform while attendance is going on. It used to be almost a period of 5-7 minutes. So I think that you can manage it. Okay. So with this, is my screen visible?
Yes, sir.
Okay, so CST Microwave Studio, let me tell you from the basics, like you need to download from the Dassault website, CST Studio. If you go to the CST, you write in Google CST Studio and download this. Last time I think I have given this instruction to you to download this student edition and run it in a system, right? Janita ma'am will share a link with you where you have to fill in detail about how many students have laptop with you, or I think it was already shared, right? It is shared
Yes.
with you. Okay. So now I think who are the owner and who are going to join with remote, please let us know. By today we'll finalize this. And then after performing the experiment, which setup you have done, the screenshot or the lab manual which you'll prepare, that should be indicating that it you have done, not your friend's copy you should do. If you're sharing, then in that case, use the team viewer, uh, and then after perform it yourself and then update this. A group of I think three or four this batch will be created. So I think today we'll do the exercise and we'll let you know. And Rita ma'am, if you have received the all outcome from anybody missing who has not given response, please check that link which
Okay,
you
sir.
shared. Yeah.
Sir, one more thing to inform them, sir.
Mhm.
Those are not having the laptop means they can join with the person who is nearby. So
Yeah, 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 yeah.
that's
If
what
in
they
the
can.
locality, in your locality, some friend or something is there, you can join with him or her, no problem. Okay, so that you take care for this performing experiment, you should use it. But I would say you can use the Teamweaver and the other system. The best thing is doing it by yourself. So make it this thing that you are able to, because you individually will be evaluated at the time of practical examination. So take care and manage it accordingly. Give the input. We will check and let you know who has not given any input. Uh, no batch will be allocated for him. That will be an issue. Okay. So with this, see you will download this and CST software you already might have used. Let me open the Studio Suite. Once you open this, CST Studio Suite, you will find a notification that student software is licensed for only personal and educational purpose only. Do not use any pirated copy of this version. Student version is fine. Here you go to the new template. Once it opens, it will ask for new template because there are several things can be done using CST Studio Suite, including electromagnetic characterization or to the static low frequency analysis or the dynamic analysis or EMI, EMC also we use this. So here you are going to use it for, because it's an antenna, you have to select this microwave and RF optical. I hope everybody is noting down and also leave this practice of only taking screenshots, which you might be practiced from last to year or longer than that. So I think everyone note down in the hand note, make a handouts for your own or notes for your subject. That's what I last time informed as well. So if you go here, you will find this antennas and select it next. Now you will find several options here, like which type of antenna we are going to verify. For example, we are going to do it for micro lab. That will do it later. Here it's starting with the basic antenna, with the wire antenna. So select it, and actually dipole antenna. Let me explain you first what is a dipole antenna. A dipole antenna is a dipole antenna is a structure which is having a feed lines. Feed lines means from which we give the input to this, and the length of the dipole here, it used to be actually any structure, any wire can be called as a dipole. If you have seen the last video, have I shown a video last time of antenna radiation? Yes or no? In the class, maybe in class I might have discussed. Yes? Can I get some response, please?
Yes, sir.
No. Okay. Then let me show you first how what is the meaning of a dipole is. Basically, any current carrying conductor, no? If we have a wire, okay, okay, and let's say it's a cross section of this wire is a circular cross section. It means a coaxial wire we are using. It's a conducting wire, and in this, if suppose the current flowing is I, and you know very well that current is what? It's defined as a rate of flow of current, rate of flow of electric charges. Generally, we say rate of flow of electrons. So rate of flow of electrons means it is already a speed. It's a speed of electron that makes a I. That's why we say I is equal to Q by T, or we can say it is Ne by T. Electron charge multiplied with the number of electrons upon T, isn't it? If we have a time varying current, and the time varying current will cause the electron to change its density, because the time varying current will be an AC signal, and the AC signal means with some frequency the amplitude is going to high, zero, going to negative, positive, like that. It means there will be a variation of the current. It means at any instantaneous value, you can say with respect to time the amplitude will be varying. And once the amplitude vary, once the amplitude vary, obviously the number of electrons, like for example, from 0 to this, the current is going to peak. From here to this, going to down 0, 0 to negative, likewise. So this electric electrons movement, okay, they used to be time varying. It means they used to be fluctuating. In the positive half cycle, for example, all the electrons are joining together at this one side, and the negative half cycle, the same electron will be transferring to this. So it means based on the time, this used to change. There will be a point zero when we can see the electrons which are generated, they will be vanished. There will be no electron when this is reaching to zero. When it's going to negative, the same electron bunch which it was there. So we can say there used to be a fluctuation. It means the electrons density, or we can say the electrons inculcating at one point used to be changing. Because of this electron, it means change of timing field, there used to be a magnetic field. If it is a constant rate, you know Faraday's law, and from Faraday's law, we can say magnetic field used to generate. That's the electromagnetic concept, electromagnet concept. So there is a number of electron, and there used to be a electric field lines in the perpendicular direction to the direction of electron, or direction of flow of current. So we can say the magnetic field will be in perpendicular if it is a static current. But if a dynamic current, we can say the magnetic field will also be fluctuating because of the current changing. Obviously, this will be fluctuating. So we can say we keep on increasing, keep on going down. It is the magnetic field also keep on increasing and down. So we can say this fluctuation in the field lines used to happen because of the time varying current. This creates the standing current ratio, okay, depending on the whatever current is there, we can say there used to be current standing wave ratio, and in direction perpendicular to this we used to be VSWR. It means voltage standing wave ratio. These magnetic field lines are responsible for radiations. So in this other sense, we can say current is responsible for radiations. How it propagates, we can talk it separately. So these two, because of this positive and negative movement, the electric field used to have E1 and E2 field, and then after this negative half cycle, it used to change. So we can say if we talk about only one half cycle, a dipole used to have two poles here and here, another pole, one and here, in between these two, and a total wavelength. Wavelength means if one cycle is here, we can say in between this is the wavelength of the cycle. From any two corresponding point, you can say. So for half of the cycle, or half of the wavelength, it changes its value of polarity. That's what the fundamental of a dipole. Okay, I would like to show you now that video. My screen visible to everyone?
The shape and size of an antenna is a function of its purpose. Wherever in physical form, it is designed to transmit and receive electromagnetic waves. Let us first consider a hypothetical antenna, the point source.
It's our nuclear
From such a source, energy
Happy New Year, sir.
radiates outwards in all directions. Let us examine this process more closely. The radiated energy can be represented by a traveling waveform of this shape. The waveform normally follows a sine curve. We will consider one complete cycle of the wave. It is defined as one wavelength. We can relate the wavelength of the radiation to the antenna which produced it.
That's what I was talking about. That one wavelength is related to the whichever antenna is producing, otherwise it's receiving. So we can say in the half of the cycle, that's you can say it changes its value, and we can say depending on the antenna, we took it a half dipole. So in that case, we can say 2 points are there.
An antenna which accommodates half a wavelength is the simple dipole. If we feed a signal to this antenna, an electron flow will be set up within it. The electron flow first produces a maximum concentration in this direction, reverses, then produces a maximum in the opposite direction.
Because this we are talking about the signal which is changing, right? It's a maximum and minimum, but actually at every instant in time we can say that the electrons which will be inculcating, they will be different. At 0 point it will not be there.
Versus maximum. This cycle repeats itself at the signal frequency. This electron flow creates a fluctuating magnetic field. Let us relate the direction of this field to the electron flow. As the electron flow reverses, the magnetic field is at a maximum, and the lines of force are in this direction. When the flow stops, the lines of force collapse. As the flow reverses, the field again reaches a maximum. The lines of force are now in the opposite direction. The magnetic field thus reverses its direction at each half cycle of the signal frequency.
Are you following, everyone?
Yes, sir.
Yeah.
This is known as the H field. The strength of this field is proportional to the amplitude of the current standing wave. This current standing wave is 90 degrees out of phase with the voltage standing wave. At this instant, the antenna has a positive voltage at this end.
This is what used to happen in the inductor also. Inductor is a current carrying device. So when there used to be a current flowing into this, the voltage, you might have seen in the basic electrical engineering, RL circuit, when you used to make the sine of omega t, omega L into sine of omega t, and the resistance which used to be there. So we can say the V across the resistance, or V across the voltage across the inductor which you check, that used to be 90 degree, because it used to be sine omega t plus of theta, and the theta used to be 90 degree to convert that into sine wave, because the overall voltage will be VL. So the inductor, or we can say current, inductor is nothing but a current carrying conductor, isn't it? We just make it in the form of either spiral or something. So that phenomena also works on the same principle. that the voltage and the current, that's why here the current standing wave ratio and the voltage standing wave ratio, they are 90 degree to each other. It means they're out of phase by 90 degree, and that's similarly the electric field and magnetic field, they are 90 degree to each other.
And a negative voltage at this end. When the voltage builds in the opposite direction, the polarity reverses. This changing polarity produces an electric field in phase with it. When the voltage is of this polarity, the field is in this direction. When the polarity reverses, the field builds to a maximum in the opposite direction. This is known as the E field.
So till now in this video, it is explained that what is H field and E field. Is that clear to everyone? Is that clear to everyone? Can you respond, please? Are you following?
Yes, sir.
Yeah. So what is the idea is here is that like H field which is generated, but did you notice one important thing that both E and H field development and their fluctuation, they are depending on the time variation of the electrons, and then time variation means the field. So we can say electrons are changing. Let me tell you one example. Like if they have, you are can you imagine that you take a bike or your vehicle and start from your home and reach to a destination, and if I say that go by 60 km per hour, exact I'm telling, 60 kilometer per hour, not average velocity, I'm telling the velocity of 60 kilometer per hour. Is it possible? Is it possible you to go? And if not, why? See, when you will start your vehicle, you will go, sometime it may go to 70, it sometime it will go to 50 also, sometime it will go to 0 also. Why? Because in between when you are moving, you can't have a constant velocity. Reason will be what? If you get a speed breaker, you need to slow down. And sometime if you find no traffic, full clear road, then you will go to the you will go to the faster speed. It means I'm telling faster speed. It means variation of velocity. So similar things used to happen here. Because of this field which is existing, a motion of electron is a current, but they should be accelerated and decelerated. Without acceleration and deceleration, there is no generation of the fluctuating field. So the most important requirement for antenna is that there should be a fluctuation of fluctuating electric and magnetic field, and that can only be based on the time varying current. So time varying current should be there. It's not like a current flowing conductor will radiate. It should be a time varying current. It means AC should be there. A frequency should be there. So with the same frequency, it will create the magnetic and electric field. Could you understand the point? Could you understand? Can I say get some few yes or few no's,
Yes,
please?
sir. Yes, sir. Understand, sir.
Very good, very good. Okay. So let me continue with this. Now what happens?
The E and the H fields thus build and collapse 90 degrees out of phase with each other and constitute the antenna's immediate field. This immediate field produces the radiating wave pattern. From the antenna, we can visualize the radiation as a series of grids propagating outwards. The vertical lines are the H component, and the horizontal lines, the E component.
Let me again explain, elaborate this. Actually, when we talked about this electric and magnetic field in both the cases, Here when we talk about the electric and magnetic field, okay, which is generated, we understood. So if there is a time varying field, there will be a fluctuating magnetic field in the direction here, that we can say H, and the direction here is E field, okay. And these two, if you see in the plane, okay, it is like this, that direction of let's say it is magnetic field, and this is the direction of electric field. Now you see what I made in another plane. This is 1 and 2. Both are 90-degree to each other. If you see in the 3 space, the propagation of wave will be in the third direction, in the z direction. Let's say it is y, this is x. So we can say there is a plane here. This electric field here also going positive, 0 to positive, and coming down 0. And the magnetic field also here going from 0 to positive and positive to 0. So in this case, because both are having pattern same, though they are 90-degree apart, they are 90-degree apart from each other, but still we can say electric field going to maximum and magnetic field is going maximum, electric field also going maximum at that time. So there will be one sort of wave nature like this. Another is possible that the electric field is going positive and the magnetic field is going negative peak. If I draw it this way, that this is electric field and the magnetic field is like this, like this. In this case, what happens? Sorry, not from here. Yeah, it is magnetic field. So in that case, what will happen? If it is going positive, it is going negative here, this side. Still they are 90-degree away. So it is called as out of phase. Electric field and magnetic field are out of phase. The radiations which is occurring, okay, in the E field and H field, okay, this is the reason of radiation from this, which you have seen just now with the animation, that they are occurring, recurring, they are again stopping. Then it used to happen with the frequency of the signal, with the frequency of signal. So we can say there is an immediate electric field, electromagnetic field existing, and they keep on propagating like this. So that's we call as a continuous radiation from the antenna. Is that clear?
Yes, sir.
Okay. So that's what we can say. We can visualize it here.
Notice that the lines are at right angles to each other. That is in space quadrature. Vectorial.
Yeah, let me go back. Yeah.
Vectorially, these lines represent the peaks of the radiating waves. Notice that their direction reverses at the next half cycle. Since the peaks of these two waves occur simultaneously, they are in time phase. The traveling waves are therefore said to be in time phase and space quadrant.
You will notice that in each cycle here, okay, in the one to the consecutive next cycle corresponding to it, the electric field and magnetic field, they are changing its quality, as if then we can say E field lines here this side in the one cycle here, which you can see here, okay. Electric field is here, magnetic field is this side, and in the next cycle electric field is here, magnetic field is this side. So did you see the magnetic field which was here, which has now changed to this side, isn't it? The magnetic field and E field lines, they have changed its quality. It means just said shaping this thing. This you can know by as a pointing vector.
The polarity of an antenna is determined by the plane of the E field. To obtain a maximum signal, both the transmitting and receiving antennas must be in the plane of the E field. The direction in which the E and the H wave pattern propagates is determined by a simple rule. To apply this rule, we use any two vectors. Imagine a corkscrew action. If we turn from the E vector to the H vector through the shortest distance, the screw has advanced in the direction of propagation. This is known as Poynting's vector rule. In the next half cycle, the E and H vectors reverse. Applying Poynting's rule again, we see that the direction of propagation is unchanged. Although we have considered only peak vectors, any vector pair would give the same direction of propagation. Let us now consider what happens when the wave strikes a reflecting surface. We will consider only one pair of the peak vectors. As before, Poynting's rule gives the direction of propagation. On reaching the reflector, the E field is reversed, but the direction of the H field is unchanged.
This is what the fundamental of a dipole, that we get the outcome from this. So here we are going to make one dipole antenna and we want to see the radiation pattern. To make a dipole antenna using, I hope that video was clear to everyone, right? The E field which is generated in the half wave here and the E field generated here, okay. So we will take this length of a wire first, and let's take this length of a wire. L is equal to 150 millimeter. We'll take this length as 150 millimeter. It means we'll divide this, and in between this gap, feed lines which we say, we'll take this gap of 20 millimeter. And another one is the diameter of this wire which we'll take. We'll take 5 millimeter. With this fundamental diameter is D. With this, let me start the practical now. So we have a wire antenna. You go to next here with the wire. When we do for the thin film and thin wire and the thick wire, if we go for thin wire or the large wire antennas, for that student edition doesn't support. We are going to make a thick film, thick antenna for diameter. So time domain analysis you can keep on selecting as it was there already. Here the dimensions which you can change, like in millimeter, gigahertz, frequency, what you are operating. So as of now, just because I'm giving a demonstration, don't change anything dimension. Everything is given in millimeter, time in nanosecond, temperature in Kelvin, voltage, current, resistance, conductance in Siemens, uh, resistance in ohms, current is an ampere. These are the inbuilt parameters. You can't change it. You can change is the dimension, physical dimension of this which you want to measure. Next is, if you go to this, let me make an antenna, and that is ranging for analysis for 0 to 2 gigahertz, because I took the frequency for this. And let me find its all the pattern using this software. So I am selecting this all, E field, H field, far field, power flow, power loads, everything. And in this practical, let me define the frequency at 1 gigahertz. Is that okay? Can I proceed? This is only in creating template. I have changed this, that what frequency I am defining. Here we do in the settings of the project, we mention that at what frequency you want to observe. Go to next. Here you can mention your practical. It is a simple dipole we are making. Simple dipole antenna. And in this dipole, it's a, let's name it as a section. Which section it is? Section C or B? Section B. Isn't it? Is it section B? So I'm
Yes, sir.
saving
Yes, sir.
for
Yes, sir.
my project for my purpose in my system with this section B. After doing this, you will find that a window will open. Here you will have a graphical window. It will initialize the project based on your settings. Let it initialize. Yeah, it is initializing the application. I'm using the student edition. Please keep in mind, everyone also use this student edition only for just an education purpose. Just a minute. Let me minimize it. Here it is. Okay. So with this here, do you hold it like that? Okay, let it be here. So here what we are seeing, this automatic the default cube structure will come here, and let me define now. So for modeling we have to first model our device, and then after we have to simulate it. So what is our device is basically antenna. So here we have to define a antenna. So go to the modeling, okay, and here there is a cylinder shape. You can, because we are taking a coaxial wire conductor, so let go and click it. There is one way is either you define all the dimension first and then you define, because I want to make it with the origin. So you can go here and you can go on this right click and you open select a cylinder. So if I select a cylinder here, anywhere you put and then you put escape, if you press escape it will show the dimension it will ask for. So let me write, yes, can you hear me? Let me write this cylinder 1 because I have to make this structure cylinder 1. Outer radius, as I told you, I are taking this outer radius as a 5 millimeter, and the length, Z direction, is the length of the wire which you want to create the cylinder. So length of the wire, let me write it as a D by 2. Okay, D by 2. Radius will be D by 2. So we are taking this a 2.5 millimeter wire, thick wire. And similarly here if we take a Z of this is L by 2 minus L by 2 to L by 2, because around the center I want to make this wire as a L by 2 to this minus L by 2. It means from center it should be half here and half here from origin. And similarly from D by 2 it should be radius, so that the axis is exactly 0. I think you are getting my point here. Let me draw and show it. Actually here from this I want to draw a cylinder, right? So I should know what is the diameter is D. So I'm taking it as center as a D by 2 as origin, and the length of this wire in the Z direction. So Z is settled here as a from the center, let's say it is the origin axis in this 3D view. So here I want to adjust it L by 2 this side and L by 2 this side. Okay, is that okay? So starting from minus L by 2, it's a plane, right? So from this plane we can say minus L by 2 to L by 2. 0 to minus L by 2 here, and 0 to plus L by 2 here. So this will be creating like this. Is that clear? Can I proceed?
Yes, sir.
Okay, thank you. Okay, so with this, not moving. It's a smaller one. Okay, let me see. So here we have seen this, and then now just click OK. But here you see component, which component, which material we are using. So we are here using, we have an option to use by copper wire, aluminum wire, whichever conductor. Let me use a for this demonstration a simple PEC. PEC stands for perfect electrical conductor. Just to view this, and here you can, after doing this, go for preview. So what I've done here, D by 2, X center 0 to 0, same X center and Y center, and Z we have center, we have minimum is a minus L by 2 because cylinder we are making, and plus of L by 2 is maximum, minus L by 2 to L by 2, and that component is PEC. Preview. If you preview this, now it will ask, because the D is variable. So here we have to give the value of D, diameter. What diameter we decided? In the beginning of this I told you, what is the diameter of the wire? Am I audible? Please respond. What
Yes,
was
sir.
the, what was the diameter of wire we thought for this dipole antenna? 5 millimeter, I said you, right? So 5 millimeter we are giving. Already it will take a scale of 5 millimeters. So just write 5, and let me say it is diameter of our dipole. diameter of dipole. Okay. It will ask another parameter because there is another variable L. So L, what is the length of this? It is asking. So length I am taking 150 millimeter, and this is what length of dipole. Okay, click OK. So once you do this, can you see here in the screen? Let me press it. Okay. So can you see here? There is a dipole made here. You can go to the view and you can reset view first, and then you can rectangular zoom for this. And you see there's a rectangular portion came. Stop rotating. Zoom. Yeah. Can you see a cylinder came here? From the origin you see 0, L by 2, and could you see this?
Yes, sir.
Is my screen visible?
Sir.
Yes, sir.
Yeah, fine. So here, let me reset again to view. You can see there's a cylinder in the cubic structure. It came up, and with this, you can see here. Zoom. Yeah. Yes. From the origin, it is 150 nanometer, 5 millimeter of this length. What actually we want to cut it because we want to make it dipole. So go to modeling again. Another cylinder. Let me choose now. Okay. And here go to another cylinder. It will ask go here and again do escape. It will ask. Let me write in the cylinder 2. Okay, this is cylinder 2 because I want to cut a particular portion. So what is the idea is if we have here, what we did is there is a cylinder which we made of a particular dimension. Now in this cylinder we will again make another cylinder, and that cylinder will be of a length which is from, suppose this is the center, so from this a length, another length we will choose, and the length of this will be uh, because we want to make a gap here, so let's take it as a g by 2, and this is minus g by 2. Are you getting me? Another cylinder we want to make, but actually we do also want the diameter of this another cylinder to be same. So here in the second cylinder what we'll do is L will take as a g by 2 minus g by 2 to g by 2. G is what we can fill it, so we want the 20 meter out of this, so we can say 10 here and 10 here, like this from the center. This we want to take it out, then we can say that with two portion will be available from the center. Would you get me? Would you get me?
Yes, sir.
So we are talking about the second cylinder now. What we do here. The cylinder 2, I am taking radius same. Why same? Because the same radius of the second cylinder is also same, d by 2. So it will, because we have defined previously, if you remember, L and D, what is there. So Studio Suite has already taken those parameters and saved it. If you want to check it, you can check it here. Just a minute. Let me show you. Go to schematic. Here you can see D. It has already now knowing what is D. D is a 5 millimeter we have entered, right? So it is showing diameter of dipole, and L is already there. So if we write now anything L another, it will be overlap with this thing. So we don't want that to overlap. Go to 3D again, and here go for another cylinder, and let me do this another cylinder as cylinder 2, and the cylinder 2 diameter is same, d by 2, uh, d by 2. Center is still same because I want to overlap the same cylinder. but the portion I want to take it out. Z minimum, let me write as a minus of G by 2. Here I am defining another parameter G. So it will ask this time when I will preview it, it will ask me now the parameter for, yeah. Now when I will preview this, it will ask me the parameter G by 2 here, and this is plus of G by 2 from the origin, right? So minus G by 2 to G by 2, because D is new. D and L already the system knows. So here, when we'll preview, and let me make that component 2 with the, let me write as a component 2, and this component 2 is suppose vacuum. Vacuum means there's nothing. We want to cut it out, that portion. So let me take that setting cylinder as a vacuum. Preview. It is asking for G, isn't it? Isn't it? It is asking for G. It means which portion we want to take it out. So that portion which we want to take out from the origin, what is the length of that G? G, if I keep the same 150, you can say whole cylinder will become vacuum. But actually I want to take out of this previous rod, previous wire, only a portion. So let me take as a 20 millimeter, and let me call this as a gap of dipole antenna. Any problem? Any problem till now? Is that okay? So once I do okay, and that's it. I've chosen the component vacuum this time, d by 2 minus g by 2 to g by 2, and let me preview. Okay, it is okay. Let me press OK. Can you see there is a highlighted portion came here? Yes? Did you see? Is my screen visible?
Yes, sir.
This highlighted portion is the second cylinder, which is of same diameter of this first cylinder, gray color, which you can see. But the another cylinder which is coming, this cylinder is of G of up to this line. No? Just let me show you. This length from here to the origin is 10 millimeter only, and similarly here is 10 millimeter, and that's why total is 20 millimeter, and this total length from here to the center, it was 150 divided by 2, it means 75, isn't it? 75 mm here, and from origin that similarly that side is 75 mm. Total is 150. So out of 150 millimeter, we have taken out this 20 millimeter out, and we want what? We want to remove this. So for removing this, there is an option you can see, none to all. What do you want to do? We want to cut away. So here is a cut away highlighted portion, or highlighted portion is this cylinder. It asked immediately after putting the value of G. So if I cut away, can you see that portion is removed now? Yes? Can you see that? At least say yes or
Yes, sir.
no. Yeah. Go to view again. Let me reset. Can you see? Okay, I don't want this written content. Let me remove this portion. Okay. So we have got this now. Okay. So here let me again zoom, and you can see the particular dipole, what is the structure. Yes? And you see from the origin there is a dipole structure happen. So we have modeled our device now. We have modeled our dipole antenna here in the CSV. So now what we want is these two portions which are here and here, these two sides, we want to simulate them. And for simulate this, first of all, we need to check it. What is that simulator we are using? Go to simulation, and here there are options like we decide the port now. So 1 and 2, because it's a dipole, so there will be only one port from which we are taking the output. Port means what? You know basic definition of port? A port is of any circuit, like we said in transmission line, 2 points are there. So if you take one as a one, if you are giving the from which we are giving input or taking output, likewise. So if I connect a sinusoidal source here, right, you know there is a one phase and one neutral, so these two together are making one port, right? We don't have, it's not a multiple antennas that we are using one antenna, second antenna, third antenna, like this, and taking output somewhere. We are analyzing only one port, only one port here. So there is one and one is ground, or we can say both are plus or minus. So there will be two field, E1 here, E2 here, and these two field we want to define them as a one port. E1, E2 are one port, and with respect to that, we are defining the definition and taking the output. Is that clear? So please note down. I think you are noting down the steps also. Are you noting down the steps? Yes, no?
Yes, sir, we are noting, sir.
Very good, very good. So here you can see in the simulation, you can see waveguide port and discrete port. Two ports are there. So go to this discrete port. You can select this discrete port. You can use any one, but let me use this because of wire antenna. I'm using a discrete port simply and define this port name as a one. See, one time you are doing in the CST studio, it will consider. So that's why don't press OK immediately. What we have to do is, because you know at lossless transmission line, and we have chosen a perfect electrical conductor, for transmission and for this, the input impedance of a device, lossless transmission line, you can follow the communication fundamental or the transmission line fundamental. From that, you know that impedance used to be 73 ohms. So here change the impedance from 50 to 73 ohms. That's it, nothing else to change. That's it. And this is apply. Length of the port is not 0. Where is the length? Okay, because we have done it, let me go to schematic here. L we have not defined here. Let me define here Z0 is equal to 73 ohm, and then okay, let me name it as a gap. It is a impedance, antenna impedance, and then okay, and here go to 3D view again, and here we want okay, we have not defined this. See, before to this simulation, please go back to one. We skipped one step. We have done modeling, and after the modeling, you have to still do one more thing, because which one we want to put. There are one side, this conductor is there, this conductor is also there, this side. Okay, here and here. So what we are going to do is go to pick and select the pick edge. And let me select this. You can see this red color will come, and here you select it, double click here, and similarly view, rotate, and the another side also. Here one more pick, go to modeling, pick, because we have to select the pick which we want to select as a or port. So I have selected now two ports, and then go to simulation now. Is that clear to everyone? Because we want this and this, E1, E2. I think if I can zoom it more, let me show you, just a moment. Zoom. And you see there are two field it is showing, E2 written here, E1 here. Because once I picked it, it is considering edge 1, edge 2, and there are two fields here. Now with this, go to simulation again, and here you can select it. Discrete port, and the discrete port, it will ask which port. We have named it as port 1, and here now change the impedance, 73 ohm. Apply. Okay, so it has taken, you can see immediately it will show in between them port 1 and port 2. We have only called this as a one port between these two, 73 ohm. Any problem?
No, sir.
No problem, very good. So here
Sir, please repeat the last step, sir.
see, modeling was okay. You
Yes,
have
sir. After selecting the discrete port.
okay, discrete port once you selected, in that after picking this, actually once you select it, these two, one red circle will come here, 1 and 1 2, and then go to simulation. In the simulation, go to discrete port, See, if I'm doing it now, it will show port 2 because already one port 1 was given up. Can you see in this pop-up window? 2. Because I have already defined in my system currently. So it is not showing. Once you will do first time, it will show port 1. Anytime if you want to remove the old history, you can go to history and you can remove this. Let me show you once again. Go to modeling, go to history, and I defined it now pick edges. So pick edges, seventh step I did it. Are you getting me?
Yes, sir.
Pick edge 8 state. Let me delete this and then again show you. Uh, hmm, Here it is delete, and yes, I deleted it, and now update this again, and now I'm again back to this position when I stored. Now let me show you once again. Okay, any problem up to here? Selected to pick edges.
Yes, sir. I
Modeling,
came up.
okay, it's fine. Now in go to simulation, go to discrete port, it will ask port because it is again showing 1, right? Because no port is defined before. And let me just make it here impedance as a 73 ohm. Why? Because that lossless transmission line used to have impedance of 73 ohm. Do you remember this? Yes? For a lossless transmission line of conductors, when we make a transmission line, Z is equal to R plus j omega L by root of, from that formula we calculate the root of j omega L upon G plus j omega C, isn't it? Anyways, that theory not required as of now. But the thing is, this impedance will be there, characteristic impedance of transmission line will be 73 ohm. Apply. Okay. Once I did it, can you see this screen? This will show like this. Once the port is defined, it will show like this. And now simply go to simulation. Okay, go to here math setup solver, and here ask this to solve setup for you. It is asking other things, nothing to change here, already it will come. Minus 40 dB accuracy for this, store this data, cache, everything whatever you're asking. Okay, start and apply. Sorry, apply and start. Okay, I did it. It is running. Janita ma'am,
Sir?
yeah, I will take just 10 minutes break.
Okay, sir.
Okay. By the time let everybody reach it, this point, recall these points, and I'll get back to this. Is this
Okay.
okay, everyone? See, it is simulating now. I'm not doing anything. After doing this, my dipole is getting simulated. So, but we need to define these things, and this is the reset view. Yeah, it is successfully completed. There are two warnings were there, no problem, but it's successfully completed. My antenna has been designed. Once you find that it is done, you will find in the left hand side here the results available with us. I will talk about these results after 10 minutes. Right? Let me meet you again at 12:17. Is that okay, everyone?
Sir,
Okay, fine.
sir,
Yes, please.
sir, once show this Z value, sir, in schematic values, sir.
Yeah, value schematic. You can see
Yeah.
G is 20 millimeter.
Okay, sir, thank you, sir.
Okay. Hello everyone. Am I audible? Hello. Can you hear me?
Yes, sir.
Can we continue from here? Everyone back? Yeah. So we have simulated this dipole structure. How did you find? Interesting, right? If anybody having already the CSC studio, I think anyone who is doing simultaneously with me or just noting down currently? Hello?
Sir,
Yes.
doing simultaneously with
Doing very good, very good. So with this, if we want to see this results which is coming from this device structure, we can see all the results of this structure which we have defined. Let me go to S parameter, right? So here we can see this S parameter in 1D results. If we see, it can show you as one
Sir, you are
parameter.
not
Sir, your
sharing, sir.
screen is not shared, sir.
Just a moment. Is it visible now?
Yes, sir, it's visible now.
Yes, sir.
Yeah, so you can see this S parameter which we are observing here. I just clicked here in the left hand side. 1D results are there. Let me do it again for you. 1D results in the left hand side. Go to S parameter, and if you click, see, it gives thousands of results. This is the advantage and disadvantage of simulation, that we get several type of, because the math solver solve all the equation. It gives, you remember, we have defined in the beginning a frequency of 0 to 2 gigahertz. So you can see the graph between 0 to 2 gigahertz we received here, right? Isn't it? For the S11 port, it means when we are giving input 1 to this, and what will be S11 parameter. So for this, we got this as a transmission line S1, because S11 only is defined, no other parameter is defined. S11 means port 1 is given a RF source between 0 to 0 to 2 gigahertz. So what is the outcome from this? This we observed here. Now, can you see one interesting thing, that what we are observing here is not 1 gigahertz. We defined it for 1 gigahertz. We defined it for, we wanted to see it for 1 gigahertz. So it means there is some problem with our dimension, L, D, whatever we messed, right? So it means the length of the dipole is not so chosen. So let me do some correction for this. Okay, you can right click here and you can go to axis marker to minimum. Can you see here it is showing 0.898. My actually device is showing the result for a frequency that 0.898, it is coming as a as parameter results for this, right? S11 is 52 dB in this case, right? So what we can do is, if I want to correct it, go back to our schematic, and let me go to schematic, and let me define a parameter here, CTE, and let's say the CT is what, at 0.898, it was showing 0.898, not exactly this thing. So let me define 0.898 divided 1 by 1, and let me call this as a ratio, because I want to see this for frequency 1. So we want to change the length also. So what we can do is, here you can define a parameter here, 0.898 gigahertz as a frequency, divided by 1. It is, I call its ratio, and if I multiply this ratio 150 with CTE, because I defined a variable here CTE, with this ratio, my all the length and everything should change. I am putting enter. It is asking me delete the current results and then do this. Yes, I want to delete it. Okay, I deleted the result, and now go for again start simulation. But before that, sorry, it has not taken it. Sorry. We have to do F7. We'll check it once again. It is simulation again started, because I changed the length, no? So my whole device length should also change now. Now again, keep in mind, 150 was the length of the cylinder which we used. And we want to observe the result for 150. So is it coming? We want to check it. Let me wait for time being. Yes, we are getting the result now for 150. Can you see the corrected value came here on the
Yes, sir.
screen? Corrected value of S parameter is coming 150. So you can see for corrected value this what changes has come. So you can go to schematic and not schematic, sorry, results, and in the result portion it is showing that the length is, yeah, here you see in the box it is mentioned clearly. The length is not 150 millimeter. To observe this result at 1 gigahertz, we need to take this value of L is equal to 134.7, isn't it? So I just made a ratio and I changed the length accordingly for this frequency which was achievable before, and I changed it to 1 gigahertz. It means this S parameter for this, I just put the value as 0.38 divide 1 some ratio, and I changed it into CTE and multiply it. Was this clear to everyone? Yes, no?
Yes, sir.
Okay. So now we got the result that L should be 134. Somebody has unmuted. Please mute yourself. Yeah. So you can see that in this case, we got the value of the L equal to 134.7. Let's see other results also. Other results in 2D, not only 1D, in the 2D also, let's see what is the energy and the power, VSWR. It gives several results, you can see. So you can take these results and screenshot of your design. Let me go for 2D result and let me see what is the E field, right? So E field of my device, it will open up here. Can you see this E field here of the dipole which we have seen? It is varying for this. We can do the simulation setting for different values. Otherwise, what we can do is right click and animate field. Can you see the animation of the field generation here with the frequency?
Yes, sir.
Yes. So this is also the field generation. We can see if you want to see magnetic field here, let me see H field also. H field of the device. Uh, Let me make it more larger for your visibility. Animation is coming. Can you see this cylindrical shape is there and the field variation from this? From where we have broken it, the field variation it can animate. If we don't want to animate, we can stop animation. We have stopped animation. We can see this. You can go to view. You can minimize it, reset view, and here you can see the output. If we see power pattern or the power flow. Okay, another important thing is far field, near field. I will talk in the class about this. What is far field pattern and near field pattern? These are the far field pattern which we are getting in the class. We will discuss about this. Okay, could you get this idea of designing demonstration of antenna here? Everyone? Yes? So we have
Yes, sir.
designed a dipole today and we have simulated using CST Studio. I want every one of you to design this week and in the Google Classroom, I think I shared with you a classroom link also. So join everyone and upload this practical results which you have received for a frequency defined at 1.1 gigahertz. Okay, design a dipole and define that frequency at 1.1 gigahertz. Gentleman, who is there? Who is unmuted? Okay. So did you notice this? Is this fine? With this, can I end up this? You can find all the results here. You can take the screenshot of pattern. I want the E field, H field, magnetic field, static pictures, screenshot from you, defined at 1.1 gigahertz. Design a simple dipole. Also check the efficiency of the project. Okay, efficiency of power, energy, everything you can see in the 1D results here because we defined only one pole. With this, I would like to end up this lab And now, Janita ma'am.
Sir.
Janita ma'am,
Yes.
can you hear?
Yes, sir.
Yes, ma'am. Take the second hour attendance and
Sure.
enter, please. Yeah.
Okay, sir. Okay, sir.
Yeah. And any doubt, anyone, before to this? We start attendance. Any doubt? Any doubt? Please let me know. You can ask it, no problem. Whichever point is the problem difficulty. No. If no, then at least yes should come. That is fine. Everybody understood? I want to hear at least 10 yes. Am I audible? I'm talking to section A. Sorry,
Yes, sir.
section
Section G, sir.
section B. So I'm telling you, if there is no doubt, please say no doubt, yes. Either is yes, yeah. If doubt is there, please let me know. At least respond to your teacher. Any doubt?
No, sir.
Few more? No?
No, sir.
Good. You got this idea, right? Yes?
Yes, sir.
Yes, sir.
Those who are not sleeping, they can also say yes. Others, anyone? Any problem? Everybody has mic problem. How you will give your attendance then? Rudrapati, any issue?
No, sir. No issue, sir.
Very good, very good. Uh, Animasati, Manikant,
Sir, no issues.
could you
Sir,
understood?
no
Right, right,
issues.
right,
Yes, sir. Yes.
right. Good. Okay, I'm happy that you got it. Okay, we'll discuss about this in the next class about the next lab. Okay, you have to submit your lab record time to time. It's a continuous evaluation. To keep in mind, we'll be checking those reports and that will be included in the evaluation as well. Chirala, Ajay Kumar, any issue? Any
No
problem?
issue.
Very good. Kondimareddy, you got this? Okay. Kondimareddy,
Yes, sir.
yeah, you got the dipole design?
Yes, sir.
Good. Kalera Shyam Mohan,
Yes, sir.
any doubt?
No, sir.
Good. Pujari Lokesh,
No doubt, sir.
okay, thank you. Okay, ma'am, you can take attendance. I am very happy that they got this. We'll continue with this newer design in the next class. Okay. You have to write in the lab report. You're about the CST project, basic from manual. You can take some theory related to this dipole theory. You have to write. You have to write it yourself. I won't share your lab manual, something like that. But what used to be the important part of the practical that must be there, the aim of the practical designing and simulation. I will share with you the course plan title exactly. You can use this, and then design your L value and this thing for 1 gigahertz. You have to design it. 1.1 gigahertz you have to define it. So you have to correct your values later on. What I showed in the same way for the values which you are getting, right? Define that cylinder in a way, a dipole in a way that it gives the value for 1 gigahertz. Thank you very much. Ma'am, please take the attendance and
Sure,
then after
sir.
let me know so that we can stop the recording. Thank
Sure,
you.
sir. Sure. Students, answer your attendance. 5302,
Present, ma'am.
71,
Present, ma'am.
73,
Present, ma'am.
74,
Present, ma'am.
75,
Present, ma'am.
76, 76, 77,
Yes, ma'am.
78,
Present, ma'am.
79,
Present, ma'am.
85,
Present, ma'am.
86,
Present, ma'am.
87,
Present, ma'am.
90,
Present, ma'am.
94,
94 present, ma'am.
96,
96 present, ma'am.
98,
Present, ma'am.
99,
Present, ma'am.
205,
Present, ma'am.
13, 13,
13 present, ma'am.
17,
Present, ma'am. 17.
20.